All these sorted things turned on over there. Cool. All right. Well, welcome back for another day here. All right. There's no nano quiz today, so the room is half as big as usual. It's always nice to see you guys. Let's see. In terms of your reminders, you have an assignment due Wednesday, not Friday, of next week. I will not be here Wednesday, so remind me by the end of today. We'll try and see if we can arrange for some extra office hours or something, because I know that's. We'll see what we can do. But in any event, your homework is due Wednesday regardless. Any questions about your homework or logistical stuff? The other thing is because I'm traveling starting tomorrow night on Tuesday, again, your lecturer will be a postdoc in my research group. You still will have the nano quiz that you're promised, not to worry. That lecture will not be filmed. So if you're relying on that, which you shouldn't anyway, then you especially shouldn't. Okay. That's all the logistical stuff I got on my mind. Anything from you guys? No, good jokes, interesting stories to tell. Nothing. Killing me. Okay, so today we're going to continue our discussion of problems in animation. But today, rather than talking about skinning, deformation, and that sort of animation problem, we're going to talk about physically based animation, which is the idea that a lot of the kind of secondary motion and interesting detail that we see in a lot of animated content is really filled in by solving a physics problem behind the scenes. And so, of course, just as you've probably all learned in your undergrad physics class, which the nice thing at MIT is I guess you guys have all taken, the main governing equations for physical bodies moving around are ordinary differential equations. There's one in particular, right? F equals ma. That's pretty important here. And that'll really be our focus, is how do we build that into the virtual world for use in computer graphics systems. Okay, so for a little bit of review, remember that we talked about quite a few different types of animation systems that are out there, right? There's keyframing, where maybe the artist or the computer system specifies a few isolated frames, and then the computer's job using splines and that kind of machinery is to fill in the motion in the frames in between. There's procedural animations. That would be, remember the example that we covered was a clock face, right? Like just a piece of code that's generating the animation as a function of time. And then today, we're going to talk about physically based animation. And remember, it's physically based because we're not going to do a particularly accurate job of capturing the physical world, but we're going to incorporate just enough of it that we get a realistic effect, right? And so today, we're going to talk about particle systems, which are a pretty common approach to physically based animation, especially in real-time physics world, like in video games. And that'll be enough to get fairly complex phenomena without a ton of computation time, right? Things like smoke, water, fire, sparks. And we're going to see that the way that they're derived is in a kind of a heuristic fashion, where we're going to stand back 10 feet and say, like, okay, like what kind of path do sparks tend to follow? And can we come up with a computational model that imitates that? Right? So we're definitely not building from first principles here. And then in our next class, actually I guess in Ed's next class, we'll cover one very specific model, which is for simulating cloth, which is what you'll implement on your next homework. And we'll see that basically cloth is more or less an extension of the particle system that we'll cover today, just with very carefully chosen particles and forces. And this is really the tip of a giant iceberg. I mean, you can teach multiple graduate level courses on all the cool physically based animation tools that are out there. And indeed, if you go to a conference like SIGGRAPH every year, there's many more that get proposed. Some to capture very detailed phenomena, especially in fluids, and smoke are very, very common ones to study, or things that are stable or try to accelerate the computational pipeline we already have. And so things like continuum mechanics for fluids, finite elements, especially for like deforming solid bodies, are all techniques that originated in computational mechanics, right? I mean, they come out of, algorithms that were trying to capture physical quantities for like product design, but they're exactly what we use in animation as well. If you like this kind of thing, there are many courses in finite element method in mechanical engineering, aeroastro, that are useful. We cover a little bit in my class. I believe Wojtek Matusik's class in computational manufacturing covers a little bit of this stuff too. Okay, Right, so the topic of this lecture and the next one is physically based animation, where our job is to simulate physics by solving the equations of motion. And this is enough to capture all kinds of phenomena like rigid bodies bouncing around fluids, plastic deformation, and so on. There are advantages and disadvantages to physically based animation. The obvious advantage is physically based animation is physically based, right? And so if you want to make animation that looks like the real world, what better way to do it than to simulate the physical laws in the real world? But the downside of that is that it's very hard to control, right? I challenge you guys to shuffle and pose a deck of cards and then drop it in a way that when it lands on the ground, it spells out your name or whatever. Make your mahjong tiles fall in a particular fashion or whatever. These are all very difficult things to do because, of course, physics doesn't work like that. Physics is chaotic and random, and animators don't like that. They like things they can control. Yeah, and especially for instance, if you're engineering a video game and the plot of your video game involves some particular physical event happening, right? Something falling on some character, whatever. These kinds of things can be very difficult to work out in a precise fashion. So there are many different types of dynamics out there in the physically based simulation world. The one that we'll talk about today is mostly just point dynamics. So you're thinking of the physics of a very tiny kind of infinitesimally small particle floating around in space, subject to forces like springs and gravity and so on. Of course, it's not a particularly realistic model, and you can step back and make things more complicated. So rigid body dynamics is going to add things like moments of inertia, right? Obviously, a spinning cube behaves quite differently than a spinning sphere, and so that's the kind of machinery you need to cope with that. And then eventually, we want to light the Stanford Bunny on fire, have it melt, all that crazy stuff. Then, that kind of deformation requires much more complicated models for physically based animation. One of the cool things, by the way, is that these used to be problems that were really in the domain of scientific computing, right? People that wanted to predict the future of physical systems using computational methods. Now, a lot of the state of the art in scientific computing happens in the computer graphics world because we really do care about fidelity of these sorts of effects. I mean, when you watch, the modern films, it's really indistinguishable what effects are digitally computed and which ones are done by literally pouring water into a big bucket and filming it, right? And that's pretty amazing. And so that's the sort of machinery that appears in this kind of area. So in today's lecture, we're going to be talking about point dynamics. These have been around forever, and of course they come from, all the way back from Newton and Galileo and I don't know, all these other people in Europe that study these kinds of things. And particle systems are basically, their job in life is to take a physical body, ignore its geometry completely and replace it with a point, and then solve physical laws, or maybe not even physical laws, to simulate some kind of interesting motion. And although this sounds like a really corny thing to do, most of video game physics is basically going to be these particle things that we'll talk about today, at least maybe until a couple of years ago. And really the amazing observation in the computer graphics community is that with very simple motion for your particles, you can get what appears to be quite complex behavior in your system. So for instance, here we have something that looks reasonably like a bunch of jets and fluids and particles moving around. The physical law governing this is nil. There's no gravity, nothing. I think somebody just prescribed a parabola for each of these points, and just by virtue of them all moving, it looks like a physical system. And it's pretty amazing how quickly complexity arises out of very simple rules that you can simulate and capture. So of course, if we're going to write software for these kinds of problems, there's one big equation that we're really going to worry about in this course. I think you've seen it before, I hope, which is F equals ma. And really, of course, this is Newton's third law, second law, third law. One of Newton's laws, fourth law, fifth law, Newton's fifth law of physics and the universe, which I think is the technical phrase, is governing the motion of particles, right? And what it says is, if I total all the force on a particle, that up to a proportionality constant, which is mass, gives us the force, right? So in a particle system, there are a couple of vocabulary words that are worth noting. A particle system has a bunch of things that are generating particles. So for instance, let's say I want to simulate a sprinkler, right? What does my sprinkler do? It has a head sitting on the ground somewhere. And it's shooting out little particles that are like little drips of water, right? So the head of the sprinkler we would call an emitter. So it's the thing that's generating these little points of mass that are going to move forward. There's external forces like gravity that are just coming from the outside. External forces don't have to be gravity, by the way. It could be that actually the artist just designs a force field that makes for interesting behavior of the particles. That's perfectly fine. Can't do that in real life, but you can do that here. And then what we're going to say is that we integrate the laws of mechanics to get motion, right? And of course, the word integrate here is really critical. F equals ma is a differential equation, right? In particular, a is the acceleration of a particle. What we care about is its position, right? Acceleration is the second derivative, so we got to integrate to get rid of that. We're going to talk about many integration strategies today in our next lecture. And then people do all kinds of stuff to get interesting artistic effects. Maybe they, randomly perturb the particles, they change their color over time, whatever. And in fact, there's like software packages out there where they'll just show little sprays of particles and they'll give you a menu of different, physical effects that you can add to them. You just slide around different parameters until you get the behavior you want. I think a lot of video game engines have that built in. Okay, so that's the basic setup in a particle system. I don't think it's terribly surprising, but there's a lot of complexity that's involved here. Like, for instance, just in my sprinkler simulation, what would be pretty bad news is if my sprinkler simulation just, I left it running overnight and it keeps generating more particles and they never go away, right? Eventually I'll overflow my hard drive. So there's a lot of little details there that we have to handle and get right for these systems to be effective. Okay, so here's an example. And you can see this particle system is fairly convincing, I would say, as sprinkler simulations go. But if you look closely, you can see the particles in the simulation. It's not too hard, right? And moreover, these particles are not interacting. The only Newton's law that's going on here is gravity. These are just a bunch of parabolas. I think actually JPEG compression is kind of helping us out here, because it's blurring out the particles a bit. But in any event, you can see that just by adding randomness and following some physically plausible paths, already we're getting interesting motion. So it's really not hard for particle systems to look pretty cool and be physically plausible. That's the phrase we're going to use a lot in the next couple days. Okay, all right, here's another one. I think this one's a little less convincing, but if you need fire, you can do it. Was this fire achieved by solving the Navier-Stokes equation, right? This famous PDE that governs fluid dynamics? No, because those are hard and we don't know how to do it. And so instead, what's going on here is, I think there's just a bunch of particles moving independently. Somebody has added a bit of a vorticity to the force field that's acting on these particles. In general, they want to move up. Maybe you just take gravity and you flip its sign because, you look at smoke and it seems to go in that direction. And moreover, I think that when they rendered, they just said, if your y coordinate is below this value, render this color. If it's in this range, render that color. There's really nothing intelligent happening here at all. And already, this kind of artist design effect is pretty good. So that's the kind of amazing thing that happens here. In fact, particle physics, as it were, is not just used for physical phenomena. Really famous examples are in kind of crowd behavior. And so a lot of times for these tertiary characters in video games and films where they're not doing anything intelligent, they're just kind of chilling and walking around so that you're in an environment with other things moving. They're actually just secretly little particles, right? They're just points with velocities, and they're just kind of, there's some walk cycle animation that's happening that's playing while they just kind of dragged along their interactions. And what will happen is that people basically are designing force fields between these particles that are modeling different effects that you might see, right? So for instance, maybe there's some radius that when I walk closer to this radius to a person, there's a strong repelling force because people don't tend to walk close to each other. Or maybe people tend to walk in clusters. So if you're within some distance, there's a force bringing you together, but not too close because then you're too close and that's weird, right? And so people will spend quite some time just designing these things basically phenomenologically, right? There's nothing scientific. But there actually is some scientific stuff. So if you look, one of the things that people do in some of these modern environments is they actually will run studies that say if I were to model human motion using, in this case, a stochastic differential equation, what would that equation look like? Can I actually sit there with a camera and watch people walking around and derive these laws? And there's some really neat studies that tell you some interesting things about the human psyche that are remarkably low level that come out of people that study these kinds of phenomena. One of my favorite ones is a SIGGRAPH paper from a couple of years ago that talks about people walking past each other in a hallway. And there's some really interesting dynamics there. Like if there's a really tight hallway, you have to solve, some version of what geometry people would call the piano movers problem. Like, I'm this wide, Colton is whatever width wide. We want to walk past each other. The sum of our widths is not this, the width of the hallway. So we both need to rotate a little bit to pass through, right? But there's like the tiniest bit of a social interaction that happens there, right? Like, do people with a particular job tend to rotate more or less, or male or female, or bald people, tend to walk forward, and people with lots of hair rotate sideways. These are all the kinds of questions that people ask in these things because they want as realistic dynamics as possible. And these are the kinds of things that often are happening in the kind of low-level processing part of your brain you don't even think about. Right? So in that case, they have these funny videos which are weirdly awkward to watch, where they have these virtual characters that walk past each other in a hallway, and they kind of follow different protocols. Like, do you walk halfway through the hallway, rotate sideways, kind of shuffle, and rotate back? And some of them are just painful, and it's really interesting to see what triggers your brain's reflexes. So these are the sort of particle systems that show up all over computer graphics. Next time, in our next lecture, what Ed is going to tell you about is cloth. Cloth doesn't look like a particle system, right? Cloth has a big square worth of material. But indeed, behind the scenes, one of the very typical ways to model, at least very simple cloth, is to just take a big network of particles and springs, which is your triangle mesh, and use that to kind of model the dynamics of the cloth. But then when you render it, you don't render it like a bunch of particles, you render it like a surface. Right? And by carefully designing this network of springs and the forces that are involved, you can kind of capture a lot of the interesting cloth behavior. Yes?
So if we just have something like that, could we just say change the force really easily and then just have a completely different
Absolutely, and that's exactly this sort of artist-directable idea, right? That maybe you want to change, for example, the material of the cloth. Is it stiff cloth? Is it, wheelie cloth? Maybe it's anisotropic, like you have cloth that bends more in one direction than another is a pretty common phenomenon. These are all things that people work on modeling. And there are different approaches, right? There are some people in cloth simulation that actually have designed these little measurement devices where you attach a piece of cloth and it just starts tugging on it in different directions and measuring the force, right? And you can just build that right into your simulation. Or maybe you just kind of say well, I have a piece of cloth. It's kind of stiff this way, kind of bendy that way. Chainmail is like that, right? Chainmail likes to bend in the direction of the chains. And then they just model that kind of phenomenologically, just make up their own physical laws. There's a wide variety. The reason cloth is going to get tricky is this what we would call a numerically stiff problem, meaning that the springs are very tight and the time steps you need to resolve that motion are very small, which gets into trouble. That also led to my favorite title of any academic paper ever, which is this, actually this creepy screenshot is grabbed from, which is called Large Steps in Cloth Simulation, which is cute because it's big time steps, and it was also sort of the fundamental research paper in this area. But in any event, these days when you look at cloth, it's just amazing the type of phenomena that you see, right? These are physical behavior. This is probably about 10, 15 years old, this video clip I'm showing you. And in order to resolve this kind of motion, now we've moved very far out of the regime of particle system, right? So here there's the forces within the cloth which do behave more or less like particles. But in addition to that, even from a geometric perspective, things are pretty crazy because the cloth bumps into itself, right? And so resolving all the forces, the interpenetration of the surface is quite challenging. In fact, if you want a good challenge problem to think about, you guys now have all worked with triangle meshes quite a bit. Can you come up with a fast piece of code that even detects whether two triangle meshes touch each other? Not so easy. Yeah, and so that is the fundamental component of what goes into this cloth simulation. Never mind that, okay, let's say I take a time step and they interpenetrate. Then what? Right? Maybe I try to undo it, but then by virtue of undoing it somewhere else on my cloth, now it's right. So you can imagine how difficult it is to solve these problems in practice. In addition to cloth, of course, another one that people really like is fluids. Particle methods do appear in fluids quite a bit. This is called the Lagrangian approach to fluid simulation. There's two approaches. I don't know, these terms you guys have heard before, Eulerian and Lagrangian. Let me explain it to you. So let's say I'm a physicist. I pretend sometimes. There's two ways to describe the dynamics of a bucket of water. Right? One of them is called Eulerian, the other is called Lagrangian. So in Eulerian mechanics, I'm like a barnacle. I stand at a point, and I have a number associated with my feet, like the density of my fluid as a function of time. Right? And so as I move around, the density evolves as a function of time, and that's what I'm going to try and simulate. So if I want to do Eulerian simulation, I would take my tank of water, I divide it into a grid where the grid cells are all constant, and then I keep track of like the flux of the particles of water moving through the grid cells, right? On the other hand, I think of water as a big collection of molecules, and I could simulate their position as a function of time. So I'm no longer a barnacle counting things moving past. I'm like a warp of the fluid system, keeping track of all the particles moving around. The second approach is called Lagrangian physics. And that leads to particle methods for simulating fluids that are really just built off of the particle methods that you'll implement in your homework. So the kind of typical techniques in that area is something called smooth particle hydrodynamics, or if you're in the know, it's SPH. And these are sort of like taking little packets or particles of fluid and simulating their motion. As you can imagine, these are really complicated and difficult to get right because fluids are not really behaving like particles that are on the scale of like, what, 1/10 of an inch or something. And so the dynamic systems that are kind of governing the motion there are very hard to get right. And even if you do get them right, you know, your particle system at the end of the day in an ideal universe looks something like this. Of course, that's not what you want to render. You want to render that, right? So you still need to take your particle system and convert it into one giant coherent blob, which is the thing you want to render, which is quite challenging. So like, here's the sorts of things you can do in fluid simulation. So this is actually a mix of Eulerian and Lagrangian, which is pretty cool. So the Eulerian is getting used to capture this sort of bulk motion of the wavy fluid on the bottom. And then of course, in this example, the sea spray off of the lighthouse is a really critical feature artistically. And so what happens is this dense fluid occasionally crashes into something and it then runs a particle emitter, which sends the particles out. And it gives that kind of cool effect. It's kind of an interesting halfway point between like pretty complicated physical simulation and totally phenomenological, like made up stuff. Like my bet is that the bulk of the fluid here is being simulated using a pretty legitimate numerical physics technique. And that these spray that's coming off of it is more or less heuristic, right? Like just sending off particles with the fluid to go fly around in the 3D scene. These kinds of computations take a long time. They're very slow. But particles also appear in video games, right? So for instance, I think the place where they're most noticeable is when you punch another character in a boxing game, as many of you maybe have done before. You know, you can see here, I guess, Pacquiao's face has a bunch of slobber and grit and God knows what else coming off of it. And each of these is particles that's just flying off in some path. I'm sure that they're not simulating any physics. And then just after some fixed period of time, they just quietly remove it. But the effects are pretty amazing. So I'm sorry this contains mildly inappropriate content in this thing, but it's actually a pretty good example of particle simulation. So this is a video game ad from a couple years ago. There you go. Okay, so it's June 30th of 7 years ago. So in order to get that kind of a video game exactly right, I mean, for one, it's got to run at 30 frames a second. But really, I think it's a coupling between two phenomena that graphics people have really struggled with, right? One being the physics, in that case, both of these particles coming off of the boxers as well as the kind of elastic dynamics. And the other being the rendering, right? That's kind of, the skin actually doesn't look so bad in these renderings, which is a pretty recent development, really. Okay. Right, and so really when you look at these particle systems, I think what you're seeing is that they range quite a bit. Everything from like actually pretty honest to goodness physical models that like a mechanical engineer has worked out really carefully to like an artist that stares at a system and writes down a bunch of laws that they think is kind of more or less the phenomena that are going on. But regardless of which one you do, whether you're trying to, simulate sweat coming off of a boxer or this like weirdly hairy animated character, at the end of the day, what you really need to do is solve an ordinary differential equation, and that's what we'll be doing in our class today. So we're going to take all these fun, cool physics examples and reduce them to something totally boring. Okay. By the way, does anybody recognize the 3D character here? No? There's a really funny data set where they took the Texas Chainsaw Murderer and they actually sliced him up and 3D scanned him so that we know his elastic deformation. Anyway, that's actually what's going on inside of it. Yep. So, right, there's a weird data set you can download. Okay, so for today, we're not going to work on him. We're going to work on a particle system composed of nice, happy red, green, yellow, blue particles. And of course, they're described with a state, right? So with every particle, we might keep around its position, its velocity, and depending on the application, maybe some other stuff, color, age, whatever. And then in every step of our simulation, we compute some forces between the particles, some forces externally, and then we integrate them in time. And the things that generate them are emitters or generators. Usually a particle has a lifetime because it would be pretty bad if you generated them, and the longer you ran your video game, the more particles you had. It's not so great from an engineering perspective. But probably the more surprising thing is that often they move completely independently of one another. And you can render them any way you want, right? Like you don't have to render them as little dots. You can render them as little flying, Angry Birds or whatever, and that's perfectly fine. Actually, Angry Birds are not particle systems, right? That is a rigid body simulator. Okay, so here's what sort of a typical implementation might look like. Maybe you store your particles in a linked list because this is an easy data structure to just keep adding new particles to, and you tend to loop over them all anyway, so it's good enough. You have some parameters that go into your particle system, like how random the initial velocity is. So maybe I'm making a sprinkler and you can generate an initial velocity in any number of directions, and how random your color is. And now for every time step, the emitter maybe generates k new particles. So it sets their positions, maybe it makes their velocity as some constant, like this is pointing straight up, plus a little bit of randomness, randomly draws a color, and then adds it to the linked list. And then now we have to advance everything in time, right? So if the particles have velocities, then how would I advance the position? Maybe I just multiply that by dt. This is not the only way to advance stuff in time, by the way, but it's certainly the most common one. Maybe I change the velocity. Remember that change of velocity is acceleration, and if you're in gravity, then acceleration is maybe gravity, yeah? And then finally you render everything, and maybe you delete some. And already the results are pretty nice looking. So let's see, I have a little demo here. So you can see that just by doing that, your particle system already is pretty convincing, which is surprising because there's nothing interesting happening here at all. Right? Okay. Right. And how do we do that? Using differential equations. Everybody's favorite topic for math class. So we're going to work a lot today on what I call initial value problems. So this is like given the state of a physical system at time t0, which we're going to call x naught, and some physical law that's governing the derivative of my system, like dx dt equals some function of x, then my job is to integrate forward in time to find x as a function of time. Right? That's the basic task in ODE, ordinary differential equations. And the ODE that we're really going to care about is f equals ma. Anybody see a problem? And you applying, let's say I have a piece of software that can solve this equation. Is it directly applicable to f equals ma? Well, let's think of the ingredients. The f is probably okay. What about the a? What is a? It's a second derivative. How many derivatives do I have here? One. So we're in a little bit of trouble. But we're not really. We'll come back to that in a second. Okay, so in other words, Newtonian mechanics are really governed by a second order ODE. When you say order, that's like the highest derivative in a differential equation. So you know the positions and forces. Your job is to give positions as a function of time. There's Newton. So what do? Let's say I have a piece of software that solves first order ODE, but I have a second order one. Am I hosed? Do I have to go back to the drawing board? Colton's shaking his head. What are we going to do? Solve it twice. Give me a little more detail.
Well, if we have both an initial velocity and initial position. So solve for a first order ODE of velocity, and solve for just the position.
That's exactly right. So let's formalize Colton's idea a little bit here. So, what is the unknown in my problem? My unknown is a function, maybe x of t, right? Which takes in time, gives me position of my particle. And maybe I'm in 3D, so this is actually the 3D vector, right? That's fancy notation for 3D. Yep. But if I wanted to, I could introduce a second unknown to my problem, just for fun, and let's call that v of t. He's also in R3, and that's the velocity of x. So, what is the relationship between x and v? Nothing too profound. What's the relationship between a particle and its velocity? Anybody? Euler? Yeah. So, x prime of t is equal to v of t. Okay. And let's say, moreover, that I'm solving f equals ma. Right? What's the relationship between v and a? The derivative, right? So what is v prime of t? Well, it's a, which is really f over m, right? And your forces tend to be a function of position, time, velocity, right? So like spring would be an example of a force that's a function of position. Wind resistance is a function of velocity. And I don't know, a spring with like somebody else wobbling around the other side might be a function of time. Yep. So let's write this in a cute way. So let's pretend that instead of having one unknown in 3 variables, I have 2 unknowns. I glue them together into one vector in R6, right? Then I can write d over dt of xv is equal to v f of, right? But take a look. Remember our prototypical first order ODE says that d over dt of basically all of your variables, the letter x here is irrelevant, right? That's just the letter we're using for the thing that we don't know, is a function of the stuff we don't know in time. Yeah? Take a look at this equation. These are my unknowns. d over dt of those is a function of those things in time, right? So I took my second order ODE and I reduced it to a first order ODE. Does that make sense? Nods? Acknowledgement? Something? Open eyes? Yeah. Okay. And so what did I pay when I did that? So I reduced the order of my ODE, but nothing is free. Yeah, I now have, instead of 3 variables, I got 6, right? And so that's basically what you pay, right? So instead of having my variable be x of t governed by a complicated equation, I have x and v of t governed by a simpler thing. So I'm exchanging, memory for computation in some sense. Yeah. Okay. Right. And so that's the basic setup that we have here. This trick of reduction to first order is a pretty common one, right? Okay. Right. And so why do we do that? Well, remember that in computer science, we're all about reducing problems to other problems. If you've ever taken a complexity theory class, you spend a lot of time traveling salesman can be reduced to quadratically constrained quadratic programming or whatever, right? You take problems and write them in terms of other problems. And essentially, we've just done that here, right? If I have a good first order ODE solver, I can use that to solve higher order ODEs by applying this trick. Cool. So that's our basic thing. And indeed, in your homework, we're going to have you implement a bunch of first order ODE solvers, because those are good enough. One thing to note, what does this show? This shows that if I have a first order ODE solver, I can use it to solve a higher order equation using this trick. What it doesn't say is that that's the best possible way to solve a second order ODE. And in fact, there are plenty, I mean, unsurprisingly, like F equals ma is a very important physical law. There are plenty of, some pieces of software out there whose job in life is specifically to solve that second order problem, and they often will outperform some of the generic methods we'll talk about here. So, yeah. Okay. Right, so this is our notation. Remember, I've kind of overloaded x. I thought of it as position, but then also it's just like the unknown in an ODE. So maybe the way we address that is we just have a capital X be like everything I don't know. And now essentially I can abstract, the right-hand side, which happens to be this special case, it's just some function f. Right? Like I don't even care what it is for this purpose. And then, my goal is just solve x prime equals f. Now, of course, if I have a bunch of particles, right, like maybe I have two particles that are attached by a spring, right, then what do? I take all their positions and all their velocities, and I stick them into one giant vector, and I can still do exactly the same trick, right? So x1 prime is v1, and then v1 prime is some function of all the positions, so that might be the spring forces and everything else, and so on. Are you with me so far? I see some like suspicious faces, but they're nodding faces. So I'm going to go with it, but you should stop me if I'm wrong. Okay. So there are a lot of different ways to visualize and think about what's going on here. One of the ones that physicists really like is something called phase space. So in phase space, here maybe this only works for ODEs with one particle, otherwise your phase space is really high dimensional. So like maybe the x-axis here is position, the y-axis is velocity or momentum, whatever. And then in that case, you can think of your ODE as like a little arrow that's telling me like, if I know my position and momentum, I know d over dt of that stuff, right? That's exactly what my ODE gives me. So it's like a little arrow that sits at every point telling me where I'm going to move. Right? And so my ODE integrator, its job in life is basically to integrate curves in this vector field. Yeah? So in this picture, notice that like the curves are making loops here. Does anybody know what this is the phase space for? Just out of curiosity. So it's some physical system where there's a position variable, and let's think about what the position is doing. It's going like right, left, right, left, right, left, right, left, right, because that's the way I should read the x-coordinate, right? And a path in here is kind of like, it's a system changing over time. So there's something going like that, and then if I give it a big enough velocity, what starts to happen? It just keeps going. Yeah? I saw a hand over here.
I was going to say, it's like kind of like a black hole kind of thing, where the event horizon is a bit like the top where you can actually see.
That one's a little complicated. That probably is true, but there's a much simpler physical system with the same property. A pendulum, right? So a pendulum, if you leave it to simulate, we'll just do that. If I whack it hard enough, it'll start spinning around in circles, right? So if you think of your angle here as, the x-axis is angle, the y-axis is velocity in angle space, right? Like theta prime. And this is exactly the phase space where below some threshold, you do that, which in this picture looks like a circle, right? Because when you're moving to the right, your velocity is positive. When you're moving to the left, your velocity is negative. That's what's tracing out this loop here. And then eventually, if you whack it hard enough, then you're like up here, right? You have a high velocity. And now your angle just keeps increasing. The pendulum's spinning around forever. At least in the absence of friction. It'll just keep spinning. Okay. Fun fact. All right, so now what we're going to talk about is numerical integration, which says I have some just for now, first order ODE, and I want to solve it, right? I want to get my position as a function of time. How do I do that? These techniques are called numerical integration or also quadrature, fancy term for that. You might have seen quadrature. I think the more typical usage of that term is like I have a function and I just want its integral, right? Which is related but not exactly the same. That's what we're doing here. So today we'll cover one very simple example. On Tuesday, Ed will cover some more advanced techniques, and of course in your homework you'll code them all. But essentially they're just different formulas. Like they're not terribly complicated. Okay, right. So let's say that I have dx dt equals f of xt. Yeah? Then, of course, if I multiply both sides by dt, then I get dx equals dt times f. Hopefully, you guys are all grown up enough to know that this expression is meaningless. But that aside, if I kind of squint at it, it's reasonable enough. And it gives me a totally reasonable way to solve an ODE, right? So I have some estimate of my current state of my physical system, that's x. What am I going to do to get it at time t plus dt? Yeah?
You find like the change in x based on by applying some function.
Exactly. I'm going to take the right-hand side of this expression, multiply it by the time step, and add that. That's it, right? So here's what that looks like in its full mathematical glory, right? So I have my system at some time t naught, and now I want to predict the configuration of my system at a new time t naught plus h. So what do? I have my configuration. I just take the right-hand side of my ODE and I scale it by h. So this technique is called Euler's method, or if you're in the know, you call it forward Euler, because there will be other methods out there that are implicit Euler or backward Euler and semi-implicit Euler and, what are some other ones? Like forward, backward, is this corrected Euler? And okay, we're big on Euler in this area. If you call it Euler, you get automatic minus 10 in this class. Okay. And in some sense, what you're doing is you're taking like a little straight line for your time between t naught and t naught plus h, right? Where this is the direction of the line and this is the sort of extent, right? So I'm like taking little straight lines. So let's see what that looks like. Right, so here's my field, my phase space maybe. So this is my ODE. I evaluate f of x comma t. That gives me some arrow in the direction I want to move. So what do? I scale that by h. There it is. And then there's my new point. Is this accurate? No, right? I mean, like you can even see here that like the integral curves of this thing are like kind of like sine waves or something. They're not straight lines, right? And so this h is somehow, some approximate step. What happens through my accuracy as h grows, most likely? It gets worse, right? Because the approximation, like essentially I took a differential relationship, but I'm applying it in a regime that's not differential. There's a positive h here. And that's where things go the tiniest bit wrong. So indeed, what we call the step size controls the accuracy of my solver, and the smaller h is typically, under some kind of weak assumptions, the better my integrator is. On the other hand, typically, I want to like predict my physical system at some fixed point in the future. Like I know my system at time 0, I want my system at time 1. So if I don't think that, maybe I take h equals 1/2, so I do 2 steps, and then I predict it, that wasn't accurate enough. I decrease h to 1/4. Notice that I now have to do 4 steps instead of 2, right? So the computational time increases with the accuracy that I desire. Okay. And moreover, we'll see that so this is accuracy. What else might go wrong? Well, it might be that this doesn't actually capture the physics all that well, or that it's actually unstable, that over time, maybe because it's inaccurate, I end up accidentally adding or removing energy from my system. Yep. So let's think about this a little bit. So here's an ODE. So this is just some differential equation on the plane, right? So it's just tracing functions, tracing paths out on the plane. Here, this is f of x comma t is minus y x. If you're really good, can you tell me what the integral curves are? Like the actual solution of this ODE? Like dx dt equals this thing. Let's logic our way through it real quick. Okay, so here's the plane. There's x, there's y. Right? So let's say at this point, what is my velocity? It's minus y comma x. Right? So what is the x component of my velocity? It's minus y, but y is 0, so there's no horizontal component. X is equal to 1, so it kind of points like that. Similarly here, well now, remember y is equal to 1, so minus y comma x is going to be like this vector, and so on, right? So if I evaluate this at other points, I get a field that looks like that. Can anybody guess the integral curves here? It's a circle. Yeah. Like that. In fact, it's easy enough to verify that. So let's say that I have x of t equals cosine of t, and y of t equals sine of t. By the way, I'm guessing this, but I'm pretty sure it's right. Okay, so what is x prime of t? Negative sine. You notice I've only ever asked you guys to actually compute like one derivative in this class. But notice that's exactly minus y. Right? And similarly, y prime. Well, that's derivative of sine. Cosine, thank you. But that's x of t. So we just verified that we solved the ODE. Okay. What does forward Euler do? Yeah, right? So let's take a look at this picture, right? So in forward Euler, like let's say I start at this point. Well, now in the first step of forward Euler, I don't move in a circular path. I move on a straight line along the velocity. So I step out like here. What do you notice? Am I on the circle anymore? No, I just move farther out. Now I evaluate my velocity. It's like that. But then I moved in a straight line again. What happened? I'm even further away. Yeah? In fact, here's a picture of what that looks like. So there's the slightly more general solution. But when you run forward Euler, it spirals out of control. Is this desirable for a video game? No, right? Like I have characters that should be like dancing in a carousel, and instead they've just like zipped off with infinite velocity into the void. Yeah? This is a big problem. And in fact, no matter how small your time step is, your solution might get more accurate, but if you wait long enough, it'll explode. Do you see that? Because no matter what, h is some positive number. I'm always going to step the tiniest bit off of that circle. What we say is that the forward Euler algorithm is unstable. It's exactly what it sounds like. What could I do to fix that? Yeah. That's exactly right. So like a reasonable thing to do, especially in an ODE this simple, might be to just project it back onto something reasonable, or like take the velocity and decrease it every once in a while or whatever. Or you can just choose a different solver. We'll come back to that later. By the way, these are not just theoretical problems. In fact, conveniently, it turns out I'm a geometry person, so I actually study a lot of problems that are related to the next couple lectures. And indeed, one of our old papers, oh God, from almost a decade ago, runs into exactly this problem. So we have a piece of software for elastically deforming 2D characters, which is something that's like built into Adobe Illustrator, these kinds of things. And here we showed that if you take some of the typical tools, and this is like this cute like 3-headed dinosaur guy, and you just take his head and you kind of wiggle it back and forth, and it's deforming in an elastic fashion, so it's like kind of roughly rotating. Then when you use these tools, if you do them in this sort of naive fashion, here the artist has dragged the head of this guy up, down, and then back to where it started, and you notice that it like tripled in size from where you began. And this is exactly this phenomenon in practice. Okay. So in our next class, we're going to talk about some more accurate and stable alternatives. And we're going to see that stability and accuracy sort of fight with each other a little bit. But for graphics, it's not clear which one is more important, right? You could have an extremely inaccurate solver that's stable, and maybe if your video game is going to be running a long time, that's actually more important than like something that in a short period of time better captures your physical behavior, but if you run it long enough, blows up. This is a topic that like is the topic of many textbooks. Where's the material? Really boring textbooks. And essentially, there are all kinds of fun ways to do this. So here, one of my colleagues at Göttingen has shown what happened with simulating a pendulum. He's done it using 3 different methods, 2 of which we will cover in this class, the 3rd of which is more advanced. But by the way, when I say more advanced, typically it's just another formula, but the derivation is yuckier. So here is explicit or forward Euler. Here they have, we'll come back to the middle one. The 3rd one is something called variational or implicit Euler, which we're going to cover in our next class. And what we'll see is that implicit Euler dampens your system. So rather than spiraling out of control, it kind of spirals toward the origin. And then finally, there's a special type of integrator that graphics researchers really like called variational integrators. By the way, you'll notice in this class we'll cover a basic method, then we'll talk about something advanced for a few minutes, and then we'll go back to the basic stuff. This is definitely in the advanced category. There's something called variational integration, where what they'll do is they'll prove a theorem that says the energy as a function of time might fluctuate. Like, it's very hard to come up with an integrator that conserves energy. But what you'll prove is that averaged over time, the energy is conserved. And so these kinds of properties are really nice for, like, I want to simulate a pendulum and walk away from my computer, and a month from now come back and the pendulum is still, doing its thing, and it hasn't like flown off the face of the earth. And so you can see even in this simple example what happens, right? So the explicit one blows up, the implicit one grinds to a halt, and the variational one just happily kind of goes back and forth. The simplest example of variational integrator is leapfrog method, which we will cover in our next class. We won't prove that it's a variational integrator. That's hard. Okay, but now that we have an algorithm, forward Euler, for solving ODE, we can go back and actually do a little bit of modeling and use it for physics, right? So of course, we got to go back to F equals ma, compute all our forces in our system, and work these things out. Of course, what is a force? I always hated this definition. I find it to be totally circular. But a force is like a thing that's changing the motion of your system. And of course, they can depend on location, time, velocity. Do forces typically depend on your acceleration? No, at least not on an inertial reference frame, right? Because if they did, then somehow it would be very hard to write down Newton's laws, right? Okay, so your forces are typically just vectors that you add together that act on a point. So, simplest force ever is just a constant. And that force is gravity, right? It's proportional to mass times, 4.81 something per something squared. And if you want to simulate smoke, maybe what you do is you notice that smoke actually more or less looks like gravity flipped upside down. So you just change the sign of that, and now you got smoke. Yeah? Notice, did I do physics? No. Did I do physically based animation? Yes. Right? So these are the sorts of things that people do. Other sort of simple forces that I'm sure you guys probably have seen more recently than I have in a classroom include gravity, right? Where, of course, the force that is between different particles is proportional to 1 over the radius squared, scaled by their two masses. Let's think algorithmically for a second. So, like, this is a force you guys have all worked with. Right? You've worked on, solved the n-body problem in your physics class, I'm sure. And now, let's say I want to simulate this numerically. I have the whole planet system, and I want to watch them all spinning around. But I want to make a video game where there's like 10,000 planets. A lot of planets in my video game. How many computations do I have to do to apply forward Euler to this system in one time step? Let's say I have n planets, in fact. I have to do n squared computations, right? Because to get the force on a single planet, I got to sum over all the other planets this value here. So if you think, like, if you're taking an algorithms course, is this like an algorithm that scales particularly well? No, right? So even though the force is fairly simple, algorithmically, this is pretty hard to cope with. Oh, so I see your hand there. That's exactly right. Yeah, so your colleague here has suggested that when R is big enough, maybe you just ignore those planets, which is a totally reasonable thing to do. How do you know when R is big enough, like, without looking at the planets? Well, you need a special data structure that can do that, right? Like, what was that?
Like
an octree or KD tree or whatever, which is actually something we'll cover later in this course when we talk about rendering. In fact, specifically for that physical system, there's a cool algorithm called the fast multipole method, which is n log n, which does this in kind of a nice hierarchical fashion, and was voted one of the top 10 algorithms of the 20th century, apparently. I don't know why I was asked to vote for this a couple years ago, but yeah. But anyway, of course, gravity is already like a good test case for graphics cards and GPUs because actually computationally it's quite expensive, even though it looks simple. So here's a graphics card from a couple years ago, simulating a pretty big n-body problem. You can see it's actually quite impressive. These calculations are happening in real time on NVIDIA GPU. Okay, right, so if you like this kind of thing, this really should be in log n, I'm sorry. But in any event, the fast multipole method is really, really, really famous technique. The only problem with fast multipole is it like kind of never works, but that's a matter for another day. But theoretically, it's really beautiful. Okay, in terms of other forces, another one that's pretty common is viscous damping, right? So wind resistance kind of falls into this category. Wind resistance, it's kind of similar to some students I've interacted with, like the faster you run, the more it pushes back. And essentially, right, this is some damping force that's minus the direction of your velocity, right? And it's perfectly easy to add this. By the way, we're talking about different ways you could try to stabilize your ODE solver, like your Euler system. One thing to do might be to add a little bit of damping, since like we kind of saw that forward Euler's job in life is to like spin you out of control. Maybe you add wind resistance so that you can't do that easily. Of course, if you add too much wind resistance, what can happen to the stability of your forward Euler?
And it just breaks down into it stops.
Well, you can stop, or in forward Euler, something really crazy can happen, which is your time step is so large, it actually, your velocity ends up pointing behind you, and you've turned yourself into a pendulum. Okay. And an additional thing that a lot of people do is they just design force fields that sit underneath their animated characters and are just constant forces sitting in space that you can't see, that are designed to get interesting behavior. Maybe they change with time or whatever. So like maybe I want, a bunch of leaves falling in the wind. So I have two options. I can either do some really complicated wind simulation, or I can design some force field that's kind of circular looking and just have it sitting in space and move around my particles inside of that thing, right? And in fact, there's some really nice ones. So there's a SIGGRAPH 2007 paper, which is a cool one, and a nice one for course projects, by the way, where essentially what they do is they just look at some physical system and then you procedurally generate a reasonable force field that's just constant sitting underneath your system to make your particles do cool stuff. And it's really incredible what can come out of this. So let's see some examples. So here, like the particles are being moved around by solving an ODE, but the forces in the ODE are just constant. They're just a function of position that's just been designed by like an artist. And essentially what these folks are doing is providing you with like little swirly vector fields that make for interesting motion, right? And actually the behavior you can get here is quite impressive really for an extremely simple method, right? All they're doing is designing just wiggly fields in the presence of this object here. I think there's a third example. Yeah. So the thing to notice is that the particles are actually not interacting with each other. They're just moving around in the force field. Okay. Right. And there are many other ones. So another kind of popular one is something called the Leonard-Jones potential, named after two physicists, where like, I feel like mathematicians behave this way. Like they want to be close to each other, but like not too close, right? So there's like some potential energy that gets better if you get within some radius, and then explodes if you get any closer. So this is kind of a useful potential for modeling. Again, it requires n-squared comparisons to compute, but there are a lot of particles that, maybe are like fluids that want to compress to a point and then, stick. And these sorts of potentials are useful there. So here you see the sort of thing that you get. Or here's another example. So these are often things that people use kind of phenomenologically to model fluids, right? So here, like maybe the blue guys want to move together and eventually they get close enough to the red one that it kind of breaks through in a phenomenon that almost looks like something is shattering, but not quite, because this is all made up and fake. Yeah. Or like here's a second example, which I think is just built out of Leonard-Jones potentials, where they've managed to simulate kind of an elastic body, right? Like these particles kind of want to hold together, and then eventually it tears far enough apart, and the potential decreases a lot, and it just falls apart. So again, are we doing physics here? No, we just have a bunch of potential energies that like make for interesting motion, and then we glue them together in ways that try to imitate the physical behavior we see around us, right? And that's the name of the game in a lot of these areas. Of course, these sorts of things get a lot more complicated in certain scenarios. So one of them is collision. We'll talk about that a little bit later. Collision is really annoying for a lot of reasons, and there continue to be new developments in just resolving rigid body collisions. Like, in fact, I remember there was the first time I taught 6837 here at MIT, there was a student who, for what she thought was going to be an easy course project involving simulating like a McDonald's ball pit. And I've never seen a student suffer so much because it is like one of the most complicated physical systems to get right, even if your balls are completely rigid, because you throw them into this pit, they want to bounce off of each other. You know, so when you do forward Euler, you take a positive step in time, so the balls interpenetrate. Right? So what do? You resolve it by like maybe moving it backward in time, right, to undo it a little bit. But in a ball pit, you have a problem, which is there's another ball sitting right here, right? So when you do that, now you intersect that other ball. There's actually this global problem you have to solve to resolve all of this motion in a way that doesn't make for your ball pit to just like collapse into a single flat, you know, ball. So, and of course, detecting when these things collide isn't terribly complicated. But if it's something like cloth, then self-collision, for example, is already just detecting when that happens is a challenging problem. There are all kinds of cool fluid solvers out there. Here's another one from NVIDIA that's kind of fun to watch. Graphics card manufacturers love to put these things out as demos because they're cool and very impressive computationally. Right, so CUDA is this general purpose programming language that NVIDIA developed for, you know, giving you direct access to your GPU. So in this case, I think there's actually a little bit of Eulerian fluid going on. Like there's some grid-based fluid simulation on a coarse level, and then they're also just throwing out particles at a fine level that are getting infected around in the velocity of the fluid. And yeah, these are real time. Like this is being controlled with like a video game controller. It's pretty impressive. Now, one thing, if you're being really picky graphics person, you look at this, is the car seems to be driving through what must be a pretty thick air, right, to get this kind of interesting motion. Notice that it's not really affecting the motion of the car, right? This is a pretty typical thing in graphics. The one-way coupling is much easier than two-way to resolve, and indeed, that's what we're seeing here. That was in 2009, it's already a long time ago. There's all kinds of cool sort of forces out there that are not particularly physically based. So two of the ones that we'll mention here are birds and fish, which is something called a Boyd, and crowds. So let's talk about the world's most kind of goofy model of what birds do. We're going to model a bird as a particle. Right? So it's just like a thing that flies. It's like a point mass that's flying around and has some velocity. It's actually not a totally unreasonable model for a bird. And now what I want to get interesting flocking behavior to come out of my particles flying around with my birds. It's kind of amazing you can do this just using physical laws. Yeah? So one of the ways that we might do that, we're going to model these things called Boyds. And we're going to come up with a couple of rules. It's the kind of thing that people do a lot in this area. You say like, well, a bird is not conscious of birds that are more than like maybe a few meters away. They can't see them. It turns out they got very small eyes. I have no idea how far a bird can see. Whatever, like a bird, maybe its flocking behavior just depends on birds within a few feet. And moreover, of course, the bird can't see behind its tuchus here, so there's some, kind of wedge sitting behind the bird that it's just unaware of. And so what I'm going to do is look and cook up a force field on this bird that depends on the birds nearby. The one that we're going to cook up is something called a Boyd. Does anybody know what Boyd stands for? Birdoid? I guess it's like a little bird robot. Okay, right, and there's a lot of different things that go in. We're not going to write the equations here, but you guys should Google it. It's really not that complicated. But essentially, what these people that propose Boyds were doing is just modeling things that you tend to see. That like, if I look at the velocity of my bird, and I look at the velocities of the birds nearby, maybe they kind of want to be parallel to one another, right? And maybe they want to be within some distance and kind of align, right? So I can just cook up forces that do that, right? If my velocity disagrees with the velocities of the birds nearby, then I can add a force that kind of pushes my velocity back in that direction. That makes sense? I think you guys could all go home and cook up some reasonable version of this And there's certainly nothing scientific about the equations here. But the amazing thing is how well it works. So here's a video from, I guess, Craig Reynolds, Dimitri Trizopoulos. You can see this is an old piece of technology. And take a look, it's like kind of amazing. So this is just being done with these physical laws. And essentially, they actually managed to capture some really interesting flocking behavior just by implementing forces between these particles that are aware of the nearby voids and their velocities. Or here's another example of a predator-prey kind of a system. So here, maybe one of the voids has more effect on the other void's velocities. Right? So, oh, I forgot it comes with a soundtrack. So this is all procedurally generated, right? I mean, these are, there's some F equals ma going on where basically the laws are just, you want to avoid the big birds and the other birds want to fly together. Or what is it, ducks fly together? Never mind. Yeah. Anyway, it's just really incredible what comes out of these systems. And the wing flapping here, I believe, is just literally like, a coded animation of just like two triangles flapping up and down. Yeah. Right, so let's see if we can play with a little demo here, because it's kind of fun. Let's see, here's the link. I played with this earlier today. We'll see if my laptop has been misbehaving on me. Yeah, so here are our voids. I believe you can throw them in here. You can see that for a while they just fly along their velocity field, and then they notice, right, like if I put one here, eventually there's some other birds nearby, and now it starts to correct its velocity to be near the velocities of these guys and flock with them. Right? So this is all happening on my laptop. So there's a link in the slides. I encourage you to play with it. It's pretty fun. And all this is happening just by basically cooking up weird forces in your system and then solving F equals ma. Right? Does this have anything to do with like Newton? Would Newton approve? No, birds don't follow Newton's laws. Like, I mean, they do, but like, this is their brain that we're talking about. They can fly, but they're not, like determining the direction that they fly by solving Newton's laws, to my knowledge. There's like probably some deep neural network going on that's really determining these things. And yet the sort of really complicated behavior that comes out. And indeed, this really is the tip of the iceberg. So one of the nice examples is in Lord of the Rings. So Lord of the Rings, I won't even attempt to summarize the plot, but my understanding is that there's all kinds of creatures that want to get in a fight with one another, and far more than an animation studio could feasibly animate. And so essentially, some modification of a particle system, probably plus some physical animation, is used to get these giant crowds of fighting whatever these are. Let's see if there's audio here. Yeah, that's okay. So my bet is that this is an extremely painful process to animate, that essentially what's going on here is that version 0 is generated using one of these animation systems, but then the front couple characters and Gandalf, I'm going to put it out there. Right, obviously those guys want to be animated by hand or even, done with an actor, and then all of this stuff has to be composited together. I think one of the things you'll notice in scenes like this in animated, movies with really heavy effects is that the camera is moving really, really fast. And that's because you're way less likely to notice a lot of the problems that would happen. Right, so there's some other details we should talk about. In a particle system, of course, there's an emitter. And you have to decide what your emitter wants to do. It probably wouldn't be a great sprinkler if it just once every 1/10 of a second shot out another particle. It'd be a little too regular. It'd be like more like one of those kind of sprinklers instead of a random one. So a very typical thing to do is maybe you flip a coin where the probability of emitting a particle increases in time until the particle is emitted, and then it goes back down to 0 or something. And indeed, all these things are totally heuristic, right? I'm just describing like fun things you could do that make interesting behavior. And so there's software out there where essentially in production tools, what the artists will do, for example, in this piece of software called Particle Effects, you can download and just design these particle forces and just preview them in real time until you get the behavior you want. So like maybe you end up with these funny spline systems where like, maybe this is their voids and like there's some force that you've determined. Notice, by the way, that these are splines again, but now the spline is in force space, right? And it's determining like as a function of radius how heavy my force should be here, something like that, right? So here's an example of the Unreal Engine.
Go to new particle system. And on the group.
Okay, here's our navigator. There we go. So
color over life is, remember we did I showed you guys the vertex color. This allows you to control the color of the particle system.
right. So this is an artist tutorial where he's just talking about all like the funny stuff that he's doing. Right. Let's maybe fast forward a little bit.
Alpha of life, so we can fade in and fade out. Yeah. 20.
So he starts tweaking with the parameters, and eventually he gets like a little thing of steam.
So X is, on the X direction is going 20, so on the Y direction I'll go in the opposite direction, so minus 20.
Right, and as he updates these things, did you notice that the smoke just like restarted and got a little bit wider? Like if we go a little farther,
What I like to do is,
you know,
the first one,
now he's added some color. And the splines that he's using are literally just like the color as a function of how far you are from the center. Right? There's no simulation going on here at all. This is just an artist designing an orange blob. Yeah? Is there a question? Okay. Yeah. Or I think if we go to the end, I don't think it gets much more interesting. Yeah. These are the sorts of things that you can do. In terms of some other details, of course, you don't have to render particles as particles. You render them as anything you want, right? So another common particle that happens in video games, sadly, is a bullet of a gun, or a laser, or a lightsaber, or whatever the heck it is that people do. And when you shoot off a particle like this, of course, your particle has a velocity, and maybe it's moving so fast that it looks like a streak in front of the camera. There are two different ways that you could do that, right? You could render a bunch of frames where the streak is moving across the screen. That's quite expensive. So instead, maybe you just stick a cylinder aligned to the velocity of your particle and render that instead. And that's roughly what goes on inside of these video games where like you shoot a gun and you see, a streak of lightning go on behind it or whatever. Similarly for motion blur, I mean, typically in motion blur, that's a really complicated optical phenomenon. Or you can just kind of know, like the particles and their velocities, so you kind of know where to blur stuff out and what it looks like. So maybe you just guess. And so here's like the difference between before and after you do that, right? So here's just a few particles, and then after you render them, as elongated objects, you get some interesting stuff. And the extreme end, if you want to render your particles, of course, you can do so using little billboards, right? So like maybe I want, I'm making my World War II video game, and I'm, fighting the Nazis and all that stuff, and I want little clouds of smoke and explosions to happen. That would be very hard to capture with particles. I mean, it isn't in the sense like in a bulk fashion. It's easy to get particles to explode outward. But if you just rendered a bunch of spheres, it wouldn't look so good. And so, do you have any guess what goes on here? Essentially, you just take a little photo of a puff of smoke. And right at the center of every particle, instead of drawing a dot, you just copy-paste that photo. This is called a sprite, or a billboard. It's called a billboard because typically it ignores the fact that as you move in 3D, it'll just kind of move to face the camera. It happens in screen space. So here's an example where they've actually made a pretty cool looking explosion. And it's just composed out of these 6 elements up here, tiled a bunch of times and resized and recolored. It's a pretty clever trick. These kinds of tricks go back a long time. I mean, one of the earliest particle systems in the 1980s comes from the old Star Trek movies. It's actually kind of depressing when you look at the history of these things. They're attached to a lot of really bad movies when they first appeared, right? I think the first fully CG frame came from that old Sherlock Holmes film. Have you guys seen this video clip with it's like a stained glass window that comes out of the wall and then fights Sherlock Holmes? You need to spend more time on the internet, people. In any event, that can lead to all kinds of interesting, behavior and particles and motion and so on. So any questions about that? These particle systems, it's really cool because these are pretty complicated behavior that really are just a few lines of code to capture. These are not complicated things. Unlike your current assignment, where it's easy to get all these transformations wrong and invert it from one another, this stuff is really easy. It's just like some formulas. And the beautiful thing is the fact that these formulas interact in such a way that you get really nice motion that comes out. Cool. All right, well, that's basically it for today. So yeah, with that, a reminder that on Tuesday, if you would like the contents of Tuesday's lecture, you gotta show up because it's not gonna be filmed. And you should show up anyway because, well, for one, you're students and you're paying a lot of money for it, and also because there's a nano quiz. Okay? So with that, I will see you in the second half of next week. Good luck with your assignments. I'll be thinking of you from the south of France while I'm eating nice food. And yeah.